so have you ever blown up a balloon? And as you were blowing up the balloon, let's just picture a spherical balloon. And as you're blowing up the balloon, you blow it up, and at first you're blowing, and you see it expand in a good bit, and then you start blowing, and you see like you don't see much change in it, and you're wondering, "Good grief, am I getting tired? I can't blow up, and it's just not changing much." Well, the reason it doesn't change much as you're going with blowing up the balloon is the further out you are, uh, that volume does not change the radius quite as much. And that has to do with related rates. Well, another thing dealing with related rates is let's fill up this cone. And we're going to see a similar thing happen here. We're going to steadily pour into this cone at 9 cubic feet per minute. It's a 10-foot high cone, and the radius of this cone is going to be 5 feet. And at the beginning, as you fill it up, it's going to fill up quick because there's less space to fill up. But the higher you get up, the change in the height of that cone filling up is going to start slowing down. So we want to figure out from the example that I gave you, at what rate is the depth of the water changing when it's 6 feet deep inside of the cone? Well, volume is 1/3 pi r squared h. Now, if you take this as it is, and if you were to do the derivative of this, you would see that you have a product rule involved. And the product rule can get really messy, especially in related rate problems. Now, there are times when it's not avoidable, but in this case, it is avoidable because we do have a ratio that's going to be consistent throughout the entire problem. The height is always, the height of the entire cone is 10, and the radius of the entire cone is 5. So because you have a linear slant on the cone, the radius is always going to be half. No matter where you are, the radius is always going to be half of the height. Now, there's something else happening here. Everything that it asks about in this problem is dealing with the height, dealing with the height, dealing with the height. So from here, I'm going to take, wherever I have r, I'm going to make it 1/2 h. Okay, so I squared h over 2, got h squared over 4, and then multiplied that by the h out here. So this is my problem, and now I'm going to do one more thing. I'm going to make this volume equals to pi over 12 times h cubed. All of that is algebra. I've not done any calculus yet. But now I'm talking about, I want to know the rate of change of the height. So I take the derivative of the entire thing, no more product rule, but both of them are changing with respect to time. So dv dt equals to 3 times pi over 12 would be pi over 4, h squared dh dt. So now we're going to plug in specifics to what's happening in the problem. We are only interested at the instant that the radius is 6. So it's going to be pi over 4 times 6 squared. dh dt we don't know. Now, the rate of change of the volume is 9. And you also have to think about what's happening. Is water draining out of the cone, which will happen in some of the problems, or is water going into the cone? So the water is actually increasing, so this is a positive value here. So it's going to be 9 cubic feet. So from here, let's do some simplifying. We get 9 equals, okay, this would be 36. 36 over 4 is 9, so 9 pi dh dt. So 9 divided by 9 pi equals dh dt. So we get 1 over pi is dh dt. Now, we have to think about the units here. All right, dt is minutes. H is in terms of feet. So it's 1 over pi, feet per minute at that instant. At that instant. That's a decimal. It's, when divided by pi, would somewhere be around 0.3, but anyway, that's what we're looking at. So that is an example of a very good related rate problem. Now, again, look through the problems that I uploaded in an email to you and see how that goes for you. There are 3 good examples. One is where you have a change in an angle. That's the problem with the Boston Marathon. And it's a neat problem to look at, but that probably needs to be the last example. First example is the most basic one, throwing a rock in a pond and watching the ripple expand. Second example there, I think after that was, someone pulling in a boat, and as you're pulling in the rope steady, the boat's going to be coming in to the bank. It's going to change depending on how far out it is. Several of these problems will use the Pythagorean theorem. That was an example of one that would use the Pythagorean theorem. So please email me if you have any questions. I'll post one more related rate problem on there, and then I will also be giving your assignment to you from your textbook. Actually, I may just hold off. I may go ahead and put the homework on there. But please do not hesitate. This is going to be a section that I have a feeling that you will have several questions about. So please email me. Let me know the problem number that you're working on, and I will be happy to help you.